Okay, so I'll be discussing our project EGP, which is entirely lab-based, by the way. Any kind of field work that we carry out is piggybacked on other projects. Skip the abstract. The project members comprise mainly of GSC staff who work in labs, and INRS, Pierre Francis. And we had a student that's from Iran that's supposed to start a while ago, but of course there's been issues with that. Hopefully she'll start this September. And we also have partners with Alberta Environment and Parks, or it's called Environment and Protected Areas now. So the project summary and objectives: higher severity forest fires lead to greater overall emissions of carbon dioxide and have the potential to release old legacy carbon and harmful constituents previously buried in deep layers of soil and permafrost. So fire severity is generally defined as the ecological impact of a fire on the environment, specifically measuring the amount of organic material consumed and the degree of vegetation and soil damage. The ability to evaluate boreal fire severity over the recent geological past would provide a much needed historical context that is currently lacking from modern estimates of burn depth. So through a series of experiments and application using dated lake sediment cores, this study aims to develop novel geochemical tools to evaluate boreal fire severity over time to inform national policies that promote adaptation and resilience in boreal communities under a changing climate. So just here's a graph to show you that you're all aware of the importance of forest fires in northern Canada. This is showing on the left, it's NRCan's database of forest fires over greater than 200 hectares from 1980 to 2023. And on the right is a recent paper that just shows you the annual burned area in Canada. And you can see that in 2023, there was an anomalous year. So one of the questions you want to address is how typical is this across the recent geological record past? Sorry, through a question?
Continue. Yeah.
Oh, that's never mind. So one of the fire markers we're looking at are pHs, polycyclic aromatic hydrocarbons. These are formed from the incomplete combustion of organic matter, forest fires, wood, for example, and they're fused aromatic rings with non-localized bonding, and they can be subcategorized into a wide variety of groups. You have on the left side, you have parent unsubstituted pHs. You can have alkylated pHs. You can have pHs with various heteroatoms in the molecule, like sulfur, nitrogen, and oxygen. And I'll just point out this one compound right here, rutene, which is 1-methyl-7-isopropylphenanthrene. That's commonly used as a marker for conifer combustion, softwood combustion. And just to highlight some previous work we've done, isotopes to pinpoint sources in source apportionment work. This is based upon work that was done over the years in the Athabasca oil sands region, and using combined dual hydrogen and carbon isotope analysis of pHs, you can use that to discriminate the main sources in this region: petroleum coke, petcoke, gasoline, diesel, so wildfire, and oil sand. So focusing on that wildfire, we're seeing we can go more in depth with isotopic analysis to kind of understand fire history better. So just a reminder of how we measure carbon isotopes on individual compounds. We combine a gas chromatograph with an isotope ratio mass spectrometer. So the compounds are separated by GC. And when you're analyzing carbon isotopes, for example, we combust them. And then the CO2 is ionized and it's accelerated down a flight tube and it's deflected on a magnet. And then you have various collectors to measure the various masses of CO2, in this case, 44, 45, 46. And similar concept for hydrogen, just different collectors. So the idea here is that using this technique we'll call it classic GC-IRMS, you can't really, you're looking at the carbon isotope value of the entire molecule itself. And an important thing to highlight is the importance of the separation of compounds. This technique and other techniques that looking at isotopes and in individual compounds requires that you have good separation, and in environmental samples, it's not always easy to get separation with background organic material and interfering compounds. And so this project has actually spent a lot of time developing some techniques to better improve that chromatography for subsequent isotopic analysis. So here's some work that I presented last year. As I mentioned, real world samples are very dirty and require substantial cleanup prior to CSIA. So the messy graph on the left shows the total ion current chromatogram, what you'd see if you analyze this in a GC mass spec, or you wouldn't want to inject that in your GC IRMS system because it'd be very dirty. Anyway, so you want to separate that. And so with some colleagues led by Shamrat Alam at the GSC here in Quebec, we developed a technique that used high performance liquid chromatography, HPLC, that you could use to help separate and purify and clean these compounds, the chromatograms, so that you can get a better signal when you're combusting that individual peak to carbon dioxide, for example, when you're getting carbon isotopes. And this was published in Organic Geochemistry last May. So an additional improvement we've been working on in the past year has allowed us to eliminate silica gel chromatography. So for those of you not familiar with this step in organic chemistry, organic geochemistry, you need this step to separate your classes of compounds after extraction, your main F1 and your F2 fractions, your hydrocarbons, your aliphatics from your aromatics. And you have to use silica gel, and you use different solvents, different polarity. And so this is very tedious, very, very time consuming. This is an example of a very big column separation right here. So we have a technique now using an instrument that was bought last year, an Extriva, an accelerated solvent extractor. It is basically self-descriptive. You, in a pressurized system, you put your sample and your silica and some sand to cover up to make up the volume in these vessels, and you can separate it. You can do your column chromatography step within the vessels themselves. So it's very interesting. It saves a lot of time and a lot of headache. So moving on to an additional development on in the lab. So I showed you the previous diagram of the classic GC-IRMS way to characterize carbon isotopes, hydrogen isotopes in individual compounds. Well, the future of isotope organic geochemistry involves orbit trap high-resolution mass spectrometry. So here, it's a GC interfaced with a high-resolution mass spec. So instead of converting your sample to your compound separated by GC to carbon dioxide, here your compounds are ionized, and you can analyze, in theory, the isotopic values of the fragments of the compounds. So you're not destroying it, you're not converting it to CO2, you're fragmenting it. And then because of the overtrap has a very, very high mass, high resolution capability, you can evaluate the abundances, the natural abundance iso ratios using that high resolution. And so this approach will allow position-specific isotopic analysis of organic molecules. And it can also, in theory, simultaneously determine carbon-13 and deuterium and other multiple substitutions of heavy isotopes within molecules. So clumping, so combinations of heavy isotopes that could reflect temperature-dependent chemical reactions and physical processes. So here's a paper, just a highlight from a paper that was recently published in Organic Geochemistry, showing the theoretical equilibrium isotope effects at temperatures ranging from 300 K to 1000 K. So why look at clumping? Well, it's to understand sources, sinks, and potentially the temperature or formation of pHs. So on the left diagram, you have the clumping of the different doubly substituted bonds in organic molecules. This is theoretical calculations. And the one on the right is just the same graph, just blown up with the scale from 0 to 6. And you can see here that as your temperature increases, your clumping decreases. So for lower temperature reactions, in theory, you'd see more clumping. That gray box corresponds to the sweet spot of pH formation during forest fires between roughly 400 and 500 degrees Celsius, or 673 and 773 Kelvin. So, that's, as you can see from this graph, some of these clumping combinations might not be very useful for this, but, they still, we want to investigate to see if this is possible to use for pHs to understand temperature formation. But of course, you can't start with that particular analysis. What we're starting with in the lab is a direct dilution technique. And so what this does, it introduces the element directly from the GC column into the mass spec without intermediate peak trapping. Because in order to get to use your Orbitrap for very precise measurements, you have to modify your GC so that you can trap and broaden your peak so that the Orbitrap can function properly, as opposed to and have a better counting of isotope ratios across the peak, as opposed to the quite narrow peaks that come out on a regular GC. So this is work done over the last year, and the black is the Orbitrap, the red is by GC IRMS, and the blue is by elemental analysis. So in cases where you had a standard, you can put it, you can measure it by EA IRMS, and you put it into a silver cup. So this is to compare classic techniques with the Orbitrap, and you can see in general, they generally agree well with the IRMS techniques, although of course there's room for improvement, and some variability is observed in some of the more complex samples, like the pet coke sample for pyrene, and also where there's not a very high signal intensity. So GC Orbitrap can provide reliable molecular average carbon-13 measurements while simultaneously preserving molecular level information. So going on to the next slide. So recall rutene, 1-methyl-7-isopropylphenanthrene. It's an important biomarker for softwood combustion, thermal degradation of conifer resins. However, it can also be generated from diagenetic degradation of conifer resins. And this can complicate the use of this compound in studies, in paleo studies. We use it as a fire marker. And so this is a mass spec fragmentation mass spectrum of the compound rutene. And in this case, you have two main ions. When you look at this in the mass spec, MZ charge 219 and 234. So in theory, you can use the Orbitrap to actually characterize these fragments isotopically. Okay, and in addition, as I mentioned before, you can also detect rare clumped isotopes, for example, two carbon-13 bonds, potentially providing insight into combustion temperature and formation pathways. So here's an application. This is work that was carried out under the Cumulative Effects program, led by Josue Jotzi. So these are lake sediment cores that were collected from Lac Ménarique in the James Bay region, an area prone to severe forest fires over the past several hundred years. And so here I'm just showing you the concentrations of rutene, this conifer marker, over time in the dated sediment cores. And on the right is the residual carbon versus TOC ratio. And that shows you when you have higher residual carbon relative to total organic carbon, you can use that to interpret that as more charcoal in your sediment, for example. So what's interesting are these two giant peaks of rutene across the core. And you often see this in a lot of samples. Now, what's the cause of this rutene? What does it mean? Is it because of very intense, severe fire history, or is it because you have a period of, or some inputs of rutene being formed by breakdown of conifer resins? And so this is where Orbitrap can become very handy for understanding this potentially. So here we have these results are very preliminary, but here we have some molecular average that is, just akin to GC-RMS analysis of rutene in this core over time. And you can see here that the carbon-13 values you see on the right axis are much more enriched during those two peaks that we see in the late 18th century and mid 19th century. So here we have the doubly substituted values of rutene. You can see they correspond with higher values, higher ratios during the peaks that correspond to the higher concentrations. Here we have the value, the carbon-13 value of the 219 fragment. And also, again, you see slightly higher ratios during those two peaks. And same thing for the fragment of 234. So if you recall correctly, that you should anticipate lower clumping at higher temperatures. This might imply that those two giant peaks of rutene in its core, in fact, aren't fire related, but they were in fact formed at lower temperatures where you have higher clumping. So that could be a signature from degradation of abiotic acid. So this has very important implications for the use of this fire marker, which is commonly used in a lot of studies. And so again, these are very preliminary results, and there's more fun work on the way in this year. Thank you.